And I guess I'll start with that. I'll start with showing the figure. So let me turn this on. All right. Hi, everybody. All right, so still thinking about it. Okay, so like I said, last two lectures, almost done. Going to talk about binary neutron star mergers this week. Going to get through as much as we possibly can, but it's largely going to be, like I said, kind of discussion based because I'm going to hit some of the highlights. And this is something that's changing so rapidly. So very little of what I'm actually going to talk about or even put on the board is from our textbook. So the textbook's got two chapters, one on initial conditions, one on evolution. Like, this is ancient history by this point in this field. In the last 10 years, it's become something totally different, right? It's just completely new over the last 10 years. And over the last 2 years, it's something completely new. So I found a nice review article, which was from like 2017. It was published in 2017. That's now also ancient history because it was before the detection of the binary neutron star merger, right? And so by LIGO, and then subsequently in electromagnetics. So, you know, this field is completely different from what it was. And so there is no textbook on this in some case, in some sense. Really, there's not. And if there were, it wouldn't be written by me. So some of this is going to be a bit ad-libbed, but that's fine. We can just talk about these things. So I have some references here. I actually found a pretty nice review article. This is this one from 2017 here. Biotti and Retzola. I'm missing a Z in Retzola, sorry. 2017 reports on progress in physics. I could have put a link in there, but I just wrote out the reference. That's a pretty nice review, and I'm actually going to follow that a little bit. It's like 66 pages long, so it is essentially, you know, a full, very robust review on the status of simulations of binary neutron star mergers. And it really will probably be the thing that I use most for the last couple of lectures here, because it's the most up-to-date sort of status report on where those simulations are. But even that is missing things because there's been a lot of progress in the last couple of years. Of course, there is a swell of stuff since GW 1708-17. We could do all of the lectures about that by itself. But we don't have time for that, so we'll focus on the simulation side of things. And I also thought that I would give a little bit of astrophysical overview, which we haven't talked too much about astrophysics in this class, actually. So that's what this figure is aimed at doing. That you've got two basic channels that you can produce a binary neutron star, right? To get a binary neutron star merger, you have to have a binary neutron star first, turns out. And there's a couple ways that you can do that. You can have sort of in situ evolution, where they start out as some sort of binary star system. The other channel is that they can be dynamically captured in a dense stellar environment, something like a globular cluster, where you've got neutron stars floating around through multi-body or three-body interactions. They become bound and they become tightly bound and very close to each other. Because not only do you need a binary of two neutron stars, they have to be sufficiently close that the gravitational radiation emanating from them will cause them to merge within a Hubble tunnel, within the age of the universe, right? Otherwise, they're uninteresting in terms of binary neutron star mergers. This diagram is from a paper by Bruce Linkska. That's what I'm going with, et al. Krzysztof Belczynski is on this paper as well, and he's done a lot of thinking about this sort of binary evolution. This is one possible and perhaps a probable, I think they argue is the most likely scenario for the evolution of the binary system that led to GW 1708-17. So you start out at the top with two main sequence stars on the main sequence, one 21 something solar masses, the other 13 solar masses, right? So two pretty big stars in a binary system. Now this is not at all improbable. Binary stars, massive stars, are preferentially in binaries. and the total mass of the binary, mass of the secondary star is correlated with the mass of the primary star. So more massive stars are in binaries with more massive stars. Does that make sense? And so having a massive binary like this, not at all unusual. 3 out of every 2 massive stars is in a binary. Others have heard me tell that joke before. So what happens, the more massive star evolves faster. And so it goes through these phases where eventually it puffs up into becoming a supergiant star or horizontal giant star. And at that point, it experiences something called Roche lobe overflow. The Roche lobes are the sort of equipotential surfaces around the binary system. It's shaped like a figure 8, where beyond that, material of the star is not actually bound to the star itself anymore. And so it's like filling up a water cup from the bottom to the top. Splashes out the top. And what happens when that outer envelope of the star splashes over those Roche lobes is that it accretes onto the companion. It actually becomes bound to a companion. So you get this mass transfer over to a main sequence star, still on the main sequence. And this thing continues, it loses a lot of its mass. So by the time that it goes to supernova, it's down from 21 solar masses down to 5. And so mass loss occurs through Roche lobe overflow to the secondary star, but also from just the winds off the surface of the star. You can see what happens to the secondary star. It gains that mass, right? It gains a lot of that mass, not all of it, but it goes from 13-something to 20-something. So now all of a sudden, you've got this sort of flip because of this transfer of mass from the primary to the secondary. Primary star goes supernova. Secondary doesn't care. Turns out stars are fairly robust. Question?
Yeah, so what's the matrix, send matrix? Units of.
Yeah, so this unit is AU. Wait, no, it's not AU. It's radius of the progenitor star, of the primary star, R naught. So this star's initial radius on the main sequence is what that is. And then down here, it's obviously less than that. And then E is eccentricity of the orbit. Thanks. Yeah, that's right. And so 0 would be circular.
Right. So I don't tell us what this is.
That's what A is, but it's somewhere in the paper what the actual distance at real units is. For some reason I thought that was AU, but it's not. It's not AU. That would be huge. I think that's the initial radius of the star. You can look that up. Okay, so the first star goes supernova. The secondary star doesn't care. It turns out stars are pretty tough. They can take a supernova blast at close range and still be fine, at least if it's a main sequence star. We're going to assume here that it leaves behind a neutron star. Probably. Maybe. In this case, it better, because we want to get a neutron star binary. This secondary star, now more massive, starts to evolve a little bit faster, goes past the main sequence to a horizontal giant star, at which point they enter something called the common envelope. The distance between them, that is going up. So who's got their computer? I'm actually confused by that now that I look at the number. I didn't look at the number before. Let me see. I'll find this real quick. I've probably still got it up on my laptop somewhere.
What was the name?
Kruslinski. Let me find it real quick. Because that number shouldn't be going up. I think that might actually be just the radius of
Is a function of the initial radius, the separation distance, units of the initial radius fixed at some point or at every stage?
Well, it has to be, I think, at every stage.
Because at that point, if your radius goes down, then the separation distance of that radius would go up. That might.
Oh, shucks.
But having a sliding scale for
Here we go. think he has another paper that.
It's cool. They don't define what they mean in the caption. It's fine. Nothing to see here. So this, you know, captions are important. Explain what you mean. Define your variables.
Oh wait, this is 11. This is 66 paper?
No, the Kruslenski paper is 22. Hold on, here we go. Wow. Yeah, it's monthly notices.
2018. How do you pronounce that name? I don't see that on here.
It's in an appendix because why would it be in the main paper?
Which on here you have to look at this.
Of course. All right, so let's go with, until I figure that out for sure. This has to be, since it's increasing up to this point, this has to be in units of the radius of one of these stars. It must be in the units of the radius of this star.
Unless it's saying R naught at every stage for one of the stars.
Because the whole time, yeah, I mean, they're getting closer the whole time. That unit confuses me.
Because at that point where it's jumping from like 251 to 254 because your radius is going down, your separation in units of that radius will go up. At that point, you're sliding that scale.
For sure, if you're sliding that
That's the
scale.
only way that makes sense.
All right, I'll have to figure this out because it's got me totally confused. The point is that once they enter this common envelope phase, that happens because this star expands to the point that it's not actually really Roche-Loeb overflow. They're actually inside of a common envelope, which is quasi-stable. This binary is inside common envelope. At that point, you lose a ton of mass, but more importantly, you lose a ton of angular momentum from the binary system. And so this secondary star loses its envelope, goes from 20 solar masses to 5, and the separation goes from some large number in some units, which we don't know, to some small number in units, which we don't know. Not much happens to the neutron star. It gains a little bit of mass, right, because it's inside this common envelope. This is interesting because if this neutron star is sort of supramassive, it might actually make it collapse to a black hole, but let's say it doesn't. So the common envelope is shed, and then the secondary star goes supernova, leaving behind a neutron star remnant. And at the point that it goes supernova, it only had 3.2 solar masses left to it. So very little ejecta. Arguably, this would look like a weird supernova. Very small ejecta mass. Very, very fast light curve. It would look like a weird supernova, but probably something like a type 1c supernova. And then you're left behind with this binary neutron star with very small separation, right? I mean, look at how this separation in unknown units goes down. I mean, it's got to be small. With 2 neutron stars there. And so now this is the system arguably that's going to sit here and radiate gravitational waves until it eventually merges. And that's what happens in binary neutron star merger. And that's sort of the next figure, which I cribbed from the Biotti and Retzola. Again, I forgot a Z in Retzola. My bad. Which is this one here. So once you form that binary and the orbital frequency goes to something like less than 1,000 hertz, things start to get interesting. Once you get within that 1,000 hertz, the loss of angular momentum of the orbit sort of becomes very nonlinear. And you almost get this plunge phase where they rapidly come together. Most simulations of binary neutron star mergers cover a few orbits, 3 or 4 orbits. That's all. You know, and they go from not touching to boop, merged, done, right? In 3 to 4 orbits. And so it's a very fast process. And they've kind of broken this out in sort of 3 possible scenarios here based on the total mass of the system initially. Up top, you've got a lot of mass. So in this case, MTOV is the maximum mass of a cold neutron star. So like what you all computed for your midterm project, TOV mass, right? So a non-rotating cold neutron star would have that maximum mass. So at top, if they're both very massive neutron stars, right? So M over MTOV is about 2, let's say, right? So maximally mass neutron stars, essentially. Once they form, they're going to promptly collapse to a black hole. And that black hole is going to be surrounded by a torus of material that, on a dynamical timescale, accretes into the black hole, right? And so down they go. It sheds off some tidal stuff from the 2 neutron stars, which become the torus. That torus has some angular momentum. A lot of the angular momentum of the binary goes into that torus. It's torqued down on a dynamical timescale due to things like viscosity, probably having to do with MHD, and MHD instabilities will cause it to accrete to this black hole. This is sort of akin and related to the idea of short gamma ray bursts and the collapse arm model. Well, not collapse arm model, but short gamma ray burst model. Okay, and then there's an intermediate stage here where, see if I can zoom in on this a little bit better. There we go. That's better. This intermediate stage where, let's say, you know, the total mass is 1.5 times the TOV mass. In this case, you're going to first form what might be called a hypermassive neutron star. Now, a hypermassive neutron star is something that has a mass greater than the maximum mass for a uniformly rotating neutron star. So if you rotate it, the maximum mass goes up. You've got some centrifugal support. But what happens for a hypermassive neutron star is that differential rotation adds additional support beyond uniform rotation to hold the neutron star up. And so this thing is differentially rotating and has a mass in excess of the comparable uniform rotating neutron star. But it persists for some very short amount of time, a few milliseconds at most, as a hypermassive neutron star that is formed. And then it collapses to a black hole, and we're essentially back to this black hole torus scenario where that torus eventually accretes and then persists as a black hole. Again, this is going to be rapidly rotating, and that's why it can withstand all that. And then there's this case down here where the total mass of the system is right around the TOV mass. Right? So potentially you could leave behind a neutron star. And so this forms a perhaps supramassive neutron star, which is a rotating neutron star that has a mass greater than the non-rotating neutron star maximum mass, so MTOV. All right, so it's held up by its rotation a little bit. Now, it could potentially lose enough mass to stay below MTOV. It's going to keep rotating, of course. It won't be spun down completely. So it's in this sort of in-between Goldilocks zone where will it stay a neutron star, or will it just get over that MTOV, lose enough angular momentum, spin down, and then collapse to a black hole? You know, question mark. So based on the initial total mass of the system, you can have very complex different scenarios. And this is just all within the case of a binary neutron star merger. We haven't even considered the idea of having a neutron star and a black hole in a binary, which is also a very probable outcome of binary stellar evolution.
Is it possible for the neutron star to spin down to a mass bigger than TOV? Since it's spinning, it would have a higher, it has a slightly higher.
Yeah, so the assumption here is that this neutron star that is formed probably does have a mass greater than the TOV mass.
Yeah.
And it is supported by its rotation.
Yeah.
Yeah.
Couldn't the final one, how much would it stop rotating?
Well, it could spin down. We know that new pulsars spin down. It's got this accretion, this torus of accretion material. One, it's coming down onto it. And two, that material is carrying angular momentum away as it leaves from a neutrino-driven wind off the torus. And this neutron star also has a wind of its own, even isolated. All neutron, it's spinning. It's going to have a magnetic field as well. We haven't even talked about MHD in this context, but that can drive off a wind as well, which can take angular momentum away from the system. And so in general, any neutron star with a magnetic field and a wind, which is all of them, is spinning down. It's losing angular momentum to its wind. And so this thing can spin down and eventually go below that threshold where the angular momentum is no longer enough to support it. Down it goes. Yeah.
How much? I would give the amount of matter that is affected in terms of the electricity.
That's correct.
How much roughly of the initial mass is in the
So there's two forms of ejecta that are often discussed these days in binary neutron star mergers. They're the prompt shocked ejecta, which happens right as the two things merge. There's a strong shock that occurs from that violent merger and sloughs off some stuff. And then there's a secondary phase of ejection due to tidal tails. And so this stuff, which forms an accretion disk around there, will kick off a tidal tail. I bet I can find a movie, which is I should have had ready, but now we can find a movie. I think David's got some movies. Binary neutron star merger tidal tail. Give me a movie. Turns out the tail is spelled two different ways. Here's Bruno, Sebastiano. All of this is press releases. Let's check this one out. Bruno Giacomazzo. Okay, let's see this, Bruno. So this is associated with GW 170817. Woof. So down it goes. Can you all see this at all? What? Why is it not? There we go. So I wasn't looking at this, but did you see the tidal tail? Did you see it? So all of this stuff, which is leaving our view, is spun off tidally. And here you have this somewhat stable accretion disk, which is fat. This formed a black hole. And the amount of material ejected in either the shocked ejecta or the tidal tail is very sensitive to the equation of state. And the last time I took a look at this, you could get almost any number you want, but we're talking up to 1/10 of a solar mass. And it is a very uncertain quantity. It's a very important quantity because it has a lot to say about our process nucleosynthesis, because if these are our process site, which they are, how much material is coming off, relatively speaking, between the shocked ejecta and the tidal tail is going to matter. And correct me if I get something backwards, because Steve will know. The shocked ejecta has lower YE. And then the tidal tail is subjected to more neutrino irradiation, and that actually tends to reset the YE up towards 0.5. And so the longer it's exposed to the neutrino radiation, the less our process you'll get. And so that prompt ejecta has quite a bit of low YE material and can make some heavy elements. But then how much time it takes to spin off the tidal tail and how much mass comes off of the tidal tail. It's very sensitive. You can almost, like I said, you can get almost any number you want. things are that uncertain. But we're talking tenths of a solar mass of stuff coming off. But details are TBD, right? I think those are the two figures that I wanted to show. Any other questions about that? Okay.
I would not move that kind of highlights the contours of the tail, but just I don't know if everyone can see it or not.
Oh yeah, this is from
But,
David's paper.
yeah, the one we
Yeah.
did on this.
That was another one that I was going to kind of review.
There's movies for these, but I don't know how they're.
Yeah. Where are David's movies?
I thought he had them on GitHub, but I'm just not finding it. But I've seen movies of this one.
Oh, here we go. That's his. That's that. Oh, found it. Movie time.
I guess it makes sense. Yeah.
Yeah, so this is now density
Yeah, it's just like,
in CGS too. So this is several binary orbits, which is kind of impressive. Now this was done with the CCZ board. Yeah. But you see that tidal deformation going on? That's also dependent on the equation of state. There you go. Whoop.
the time was on this.
Nope. Black hole.
There's that one.
Yeah, I didn't see much ejecta there. I don't think it was highlighted in that image.
No, not all of them.
Probably not that dense. So it's probably just white.
So yeah, I think that's the problem, is that we need a log scale to really see it. This one says that it develops a one-armed instability. This is the one-armed man. Anybody else get that reference? Fugitive? Harrison Ford? Tommy Lee Jones? Yeah, okay, so these wobble, and then the hypermassive neutron star gets this R mode one-armed instability, which is kind of crazy when it starts to really spin up. So see how this remains persistent, this sort of one-armed spiral instability? That is loud gravitationally. Which do you mean the one-arm instability?
Yeah,
So it's part of a class called low T on W instabilities. You can only, well, again, the equation of state matters for if you can get these things. And so T on W means the rotational energy to the gravitational energy. And if you get into the right regime, you can actually develop these non-axisymmetric instabilities which grow, which are true instabilities then. So here's the image that Steve was talking about. This actually now shows, this is in log scale. So what Halbert said was right, it's just all white. This is labeling the tidal ejecta on the merger. And so that's stuff that'll actually be shut off. Yeah. And this is a very recent paper, and this one's really nice if you want a snapshot of where modern research is. Steve is a co-author. But David did 59 of these simulations, and you can see each one of them is many orbits. And many of them go to collapse to the black hole and follow the ring down. I mean, it's the most complete. It's like, this is what, that research has been driving towards. Ooh, electron fraction. We're just going to watch movies all day. It's a clip show day, everybody. It's a clip show. Oops. So this is the electron fraction, right? And so we're looking to get low electron fraction material.
Yeah.
There we go. This is the one that zooms out, right? So there's the shock ejecta. And more comes off.
Later stuff isn't much.
Yeah.
I mean,
But you can see what's happening as more and more material gets irradiated by neutrinos, the electron fraction in this ejecta gets higher and higher.
at that point there, it's not good with our process.
No.
So the spectrum above the axis ends up being lower. It seemed like initially, at least, you had higher electron fraction on the London star, and the stuff being swung out.
Oops.
Maybe it was just the movie.
Might have been just the.
Because right there, the main stuff you're seeing coming off, that's some of that shock eject early on. You're not getting that along the station axis. You still have a lot more neutrino interactions there driving the YE up if it's closer. Later times doesn't.
All right, David. David, you have a good website. Of course you do. Woo, there's another one. Oh, this is old. All right, fine. High accuracy. All right.
Oh, wow.
I don't know what he means by this. These are from a few years ago. No. No. These are my lectures on binary neutron star mergers. We're just gonna watch the movies. I love it. I love this plan. Happy to be part of it. Oh, black hole. Oops, my neutron star fell down.
Then when you realize the time scale this is on the order. Seconds encompass the whole thing. From whatever there is separation.
Oh, hey, look. We've gone far enough that now it's to one of my papers with David. So here's a movie that I like to show. All right, that's all right. Now we've gone too far. We've jumped the shark. Okay. All right. So let's then talk about, before I show even more clips, let's do a little bit of real stuff. All right. So we'll talk a little bit about, we're going to get to initial conditions and some of the trickiness with initial conditions. But I'll also talk a little bit about some of the approaches that are taken for the numerical relativity of binary neutron star mergers. So last time, oh wow, okay. So, binary neutron stars, BNS is the abbreviation. Du jour. All right. Now, as I said last time, BSSN is the common approach, and it is, but it's not the only one. These simulations are particularly challenging because, one, must be 3D. There's no, you saw the movies. Pick out how do you reduce that to 2D. Tell me how. Some people try, right? But it's got to be 3D. So right off the bat, it's hard. You've got to have a dynamical space-time, right? You've got to be evolving the metric because it's one of the most extreme relativistic environments you can get. And so it is highly dynamical. You've got to solve for that somehow. You've got magnetohydrodynamics, right? So often we forget the M, but the MHD, the M in the MHD is pretty important. And what David was doing was MHD. And in particular, if you want to talk about shedding that accretion torus or how it's losing mass to a wind, that's often generated, we think it's generated by MHD instabilities, things like magnetorotational instability. To capture that, you've got to have the MHD in there, or do some sort of non-ideal image-dependent thing. You have a microphysical equation of state. So the equation of state of nuclear matter, of dense nuclear matter, extremely important here, right? It determines a lot of the parameters of the system. And arguably, there's no other, hey, I'm missing an L. There's no other system in which it matters more, even more so than the supernova problem. You really want to talk about how this system evolved, you need to know that. For a long time, you know, the simulation of binary neutron star mergers has gone through various stages of evolution. It's evolved rapidly in the last 10 years. The first simulations used like conformal flatness. Many of them were grid-based. Some of them were smooth particle hydrodynamics. Shapiro, one of the authors of our book, was involved in some of those. Most of them did not account for things like a microphysical equation of state. And so instead, they were using things like gamma law or broken power laws, where it was essentially a polytropic equation of state, where maybe that polytropic index varied and depended on density. So you could mock up the behavior of a real neutron star. These days, the simulations are moving to realistic equations of state, like what we use in core collapse supernova simulations. And then the other problem is this neutrino transport issue. The neutrinos, you know, like in the supernova problem, are very important. At first, there's not a lot of neutrino radiation going on, but once the merger happens and these things heat up, the neutrino radiation becomes a dominant factor in the system. And if you want to talk about the R process nucleosynthesis, the irradiation of the ejecta by neutrinos sets the electron fraction, ultimately. And that determines everything then about the nucleosynthesis that occurs. And so this is also critical. Any one of these things is hard, but you put them all together into one system. It's actually the same list of ingredients that goes into a core collapse simulation. So we all have the same problems. But the relative importance, I would say, is different. And so for supernovae, we focus a lot on this. And so if you take a snapshot of the field, and this has been historically true, you know, take 10 years ago when we really started trying to revolutionize what was going on in BNS. Supernovae were way ahead in terms of neutrino transport. The BNS folks were way ahead in their treatment of general relativity and numerical relativity. And so these two fields kind of came from those different camps. The BNS folks focusing on GR and numerical relativity, supernova folks focusing on neutrino transport, right? And then these other things were sort of equally important to us both. These two things in supernovae more so, you know, we were ahead here. And so I think one reason why BNS has evolved so rapidly is one, its importance because of LIGO and gravitational waves, but two, we started doing workshops roughly 10 years ago, bringing these two fields together, microphysics and computational relativist astrophysics. I organized one of these here at MSU a couple of years ago. And so it was really to bring these two fields together and share technology, right? Where we take the transport methods and the microphysics methods from supernova simulations and put them into the BNS mergers, take the space-time stuff out of the BNS sims and the numerical relativity codes and adapt them to be used in supernovae. And so we continue to do this. In fact, we have another micro workshop this summer that I'm helping to organize. I'm not really organizing. No, it's going to be in Jena, Germany. Sebastiano Granuzzi is the host there at Jena. So I think we've made tremendous progress in this field. And it's through this technology sharing, but we come from these two different sides of this equation. And so BSSN is pretty common. Now, last time when I did BSSN, I didn't talk about gauge choices. So let me talk a little bit about gauge choices because that becomes relevant when you actually want to do a simulation, particularly with BSSN. So the gauge that we're going to talk about. One, you're going to use something called hyperbolic singularity avoiding. And we talked about this before, 1 plus log slicing. Remember when we were talking about initial conditions, et cetera, we had to choose gauge conditions. One of them was this so-called 1 plus log. And that boils down to an equation that looks something like this. Partial with respect to time minus the shift vector, partial with respect to I of the lapse is equal to minus f of the lapse squared, all times k minus k naught, where this function of the lapse has got to be greater than 0, and k naught is the trace of the extrinsic curvature at t equals 0. And so this is the constraint that you apply, the slicing condition that you apply to the lapse. And then on top of this, we need a gauge condition for the shift vector. And so there, we talked about this as well. I think we did. Did we talk about gamma driver? It's in the book. I can't remember if I talked about it in the lecture. Here, I'm going to assume that that's correct. Second partial derivative with respect to time of the shift vector is equal to some auxiliary function, auxiliary variable f times the time derivative of the connection functions minus eta, which is just a factor, partial derivative with respect to time of the shift, where f and eta are positive functions of space and time. So these are the two common gauge conditions that are chosen for BSSN simulations. And they're very nice. This condition here tends to drive the conformal connection coefficient to 0. And remember, that's a nice condition. That's what we want. In BSSN, this scalar field represents our sort of violation of the constraints. And so we want to keep that small. This condition for the shift pushes that towards 0. When you actually go to implement this numerically, you usually solve these equations to first order. And you get something like this. So the first order implementation. We give you a set of equations that looks like this. Partial with respect to time of the shift minus shift j, partial j of the shift I is equal to 3 over 4 alpha the lapse times an auxiliary field B, not to be confused with the magnetic field. And then the partial with respect to time of that B of I minus beta j, partial j of BI is equal to partial with respect to time of the conformal connection function minus beta j upstairs, partial j, connection function I, minus eta times BI. So we introduce this BI, which is just an auxiliary variable, to solve this equation to first order, to take what was a second order equation and make it first order. And then eta acts as a damping. So that damps and avoids strong oscillations in our shift vector, is what that eta does, is to avoid those strong oscillations in the shift vector when we solve this coupled set of first order equations, right, for my shift. All right. Okay. So these two things together, the 1 plus log slicing and gamma driver gauge choice for the shift, they avoid singularities if they appear, which is nice, right? And they also if any coordinate distortions, or gosh forbid, coordinate singularities avoid, they try to, singularities appear, they try to avoid that, right? And so they damp those out essentially, right? They don't guarantee that they don't appear, but they work against the growth of coordinate distortions due to strong space-time curvature, right? And so remember, like we talked about Schwarzschild coordinates, it's got a coordinate singularity at the event horizon, bad. These gauge conditions work to avoid those kinds of coordinate singularities or strong coordinate distortions. And you saw, so the simulation movies that I showed you, most of those I don't even think were BSSN, but they're related. And the CCZ4, which I'm going to talk about in a minute, uses these same gauge conditions. So this statement is just as true for those as it is for BSSN. The simulations we showed of binary neutron star mergers, they collapsed a black hole, right? You got black holes in the grid. And they kept on evolving. And this choice of gauge conditions doesn't require any fancy excision techniques when a black hole appears. We didn't even talk about those, actually. We didn't have time. But these gauge choices mean that you can evolve that on the spacetime, and your coordinates won't reach the singularity. And your coordinates won't even reach a coordinate singularity. So you're good. Let the black hole be. It'll evolve. Happy day. And these are horizon penetrating as well. I'm pretty sure that's true. Okay. So those are the gauge choices that you'll make for BSSN. They're the same for the CCZ4. Now, Steve asked about this last time and I didn't have an answer. So this time, I thought I'd go over that real quick and provide a better answer for how that's different from BSSN. Any questions? So we use the same gauge conditions. David's work that we just showed there was actually evolved with a different approach to solving the field equations. CCZ4. This is still falling under the sort of family of ADM and 3+1 like methods to solve the equations, different from generalized harmonic coordinates, which we've obliquely referenced but haven't done on the board. So that's the other approach, which can be and has been used for binary neutron star mergers. I'm not going to talk about it. This one is more akin to our ADM equations, and so I think it is nice to talk about. And it seeks to combine some of the advantages of both BSSN and generalized harmonic coordinates into one. And so it's a fairly nice formulation, actually. And newer, even much newer than BSSN. And so this is pretty state-of-the-art stuff. And what this stands for is, let me write this down, conformal and covariant Z4. And so it's built off a approach called Z4, which introduces a new vector field, a 4-vector field, Z, which acts like the constraint violation, right? In much the way that we use the conformal connection functions in BSSN to deal with our constraint violations. Here, we introduce this new 4-vector. So Z4, you're going to deal with the elliptic constraints, the momentum and Hamiltonian constraints by converting them to algebraic relationships for a new field. And we're going to call that Z mu. I'm switching to Greek indices, otherwise I'll screw it up if I go to A's and B's and C's. All right. And this measures the deviation from the Einstein field equations. What do I mean by that? So in particular, This is derived from the Lagrangian, the covariant Lagrangian. Derived from covariant Lagrangian. Following way. And that Lagrangian looks like this. So L is equal to G upstairs mu nu all times Ricci tensor R mu nu plus 2 times the gradient mu of this Z4 vector. Okay? Like that. And so Z equals 0 in this case. If that new scalar field is 0, I'm right back to the original Einstein field equations, the precise form of the Einstein field equations. To see that more clearly, let me write down the field equations for Z4. So the Z4 field equations look like this. R mu nu plus gradient mu of Z nu plus gradient nu of Z mu plus kappa, which is just a coefficient. I probably better write that on the next line. Run out of space. Plus kappa, multiplicative coefficient on n mu Z nu. N mu is the unit vector in the time direction, like we use in 3+1. N nu Z mu minus 1 plus kappa 2 all times G mu nu in sigma Z sigma close is all equal to 8 pi all times T mu nu, oops, minus 1/2 G mu nu T. So if you stare at this, you can convince yourself that if I set Z equals to 0, this reduces back to the original form of the Einstein field equations, at least for the Ricci tensor. Right, if Z is 0. Okay. So then, so once we fold in the energy and momentum constraints, we get a system that includes an evolution equation for this new 4-vector Z, okay? With energy momentum constraints. We get an evolution equation for Z. And what that does is when you incorporate that into the system, your 3+1 scheme becomes strongly hyperbolic. Just like in BSSN. So recall that ADM, 3+1 ADM, weakly hyperbolic. No bueno for long-term evolution. BSSN makes it strongly hyperbolic by introducing the evolution of this conformal connection function. Here, we're introducing Z and an evolution equation for that, which also makes the system then strongly hyperbolic. I'm going to write the equations here. You might guess that they're long, but here they come.
How long?
How long would you like, Mayor?
I don't know. Pretty sure.
I mean, warm up your wrist, all right? Okay, so I'm going to use the Lie derivative here. When I wrote out BSSN, I actually expanded the Lie derivative. But here I'm just going to keep it in a more compact notation. So they're not as long as they otherwise would be if I wrote out the terms in the Lie derivative. So Lie derivative with respect to the shift of the 3 metric is equal to -2 alpha Kij Cool. That looks familiar. Nothing different there. Partial with respect to time minus Lie derivative along the shift of the extrinsic curvature is equal to minus gradient I alpha j. There it is again. I don't think that's correct. So I went through and fixed that in several places in these equations that I'm following along from. That's not right. That is not right. But they made that same, I think, mistake in 3 different equations. And I went back and looked at some other papers. Now I'm wondering if I'm the crazy one or they just made a mistake. All right.
Where's the J?
Well, I just erased the J. The J was here, but that doesn't make any sense because the shift is a scalar. And so I actually thought what they meant.
It should be gradient I, gradient J of alpha.
That's what I thought.
Yeah.
So in every place that they had this, what they were missing a comma. And this could have been a typesetting error by the publication. And so in every place where they had this, this is what I did. Okay. So to make the notation clearer, I'll put it here, like that. That's what I thought, based on looking up different things. Huh?
The one I was looking at here had it broken up into that's the traceless part of the trace.
Oh, yeah. No, I haven't done that here.
It's still the same when you
Yeah. And yeah, and so is this a paper with Retzola on it? I bet.
yeah, he's on this one.
Yep.
Is it a partial derivative?
So I think it's supposed to be a partial derivative. You said gradient though?
That's what they have in here. I mean, they have it broken up a little bit differently.
Yeah.
Just decomposing the 2 pieces, but
Yeah.
in both of them, it's showing gradient.
All right.
Well, for the trace, it'd be a little
Well,
possible, but yeah.
Everyone know that that's a caveat, that I think there's a mistake in those equations, and I'm confused how to correct them. All right, on we trudge. Gradient of z symmetrized with I and j, and then minus 2k downstairs I, upstairs L, k downstairs Lj, plus k the scalar minus 2 times theta, a new scalar field that we'll talk about and define in just a second, times the extrinsic curvature minus kappa 1, my multiplicative factor. But, oh, I'm going to run out of space here. Let me move this down here. Multiple lines. Kappa 1 all times 1 plus kappa 2 times this new field theta times gamma ij, close bracket, minus 8 pi alpha all times the stress tensor minus 1/2 the stress scalar minus the energy all times gamma ij.
That's square bracket by the spatial metrics on the first term of the bottom line where it's the
It's from the first line of the second term.
You think so? Hold on.
Oh, wait, no.
No, I closed that.
Blocking the-
I was blocking it, yeah. I just wrote these.
should be everything after the equal sign up to it. So,
Where did it go? Hold on. Sorry. These are not obviously very well proof. My apologies.
It should be, so where you got alpha square bracket, 3G tensor. That square bracket at the end of the line shouldn't be there. It should be closed down below. Because you have alpha times all of that.
You're right, right here.
Yeah, that one should be there.
Correct. Correct. And did I messed that up in my handwritten notes too? Okay, all right, sorry. Okay. Couple more equations. Then I'll stop. Promise. Time derivative, Lie derivative of this new field theta. So we have an evolution equation for it. Alpha over 2, all times curvature scalar plus 2 gradient with respect to j of z upstairs I. Nope, that's a divergence. Upstairs j. Plus quantity of k minus 2 times theta, all times k, minus inner product of kij, the extrinsic curvature, like that, minus 2 times z upstairs j, partial with respect to j of alpha, all over alpha, minus 2 times kappa 1, all times 2 plus kappa 2, all times this scalar theta, minus 16 pi e, close bracket. All right, my brackets match. Hooray. Last equation then for this field z, partial with respect to time minus the Lie derivative along the shift of, did I say scalar? I meant vector field. The spatial components of z, as we're now in 3 plus 1, alpha all times, gradient with respect to j of k downstairs I upstairs j, minus the Kronecker delta downstairs I upstairs j of k, the scalar, plus partial with respect to I of theta, minus 2 times k downstairs I upstairs j times z downstairs j, minus theta times partial with respect to I of alpha over alpha, minus kappa 1 times z downstairs I, minus 8 pi, the momentum vector. And now recall that here the E energy is defined as the projection in alpha and beta of the stress energy tensor T alpha beta. Momentum vector is defined as both, this is the projecting into the time direction, right? Both indices into the time direction. The momentum is defined as projecting one of the indices into the time and one into the space. So gamma I alpha n beta of T alpha beta. And then this stress tensor is projecting both into the space direction. So gamma I alpha, gamma J beta of T alpha beta. And then our new auxiliary scalar field is defined as the projection of my new z vector into the time direction, which is just equal to alpha times the time component of z. All right, and so that's the system. I have not split this up into the traceless separation, which in many implementations you will actually do, much like what we did with BSSN, where we had the A tilde and split the extrinsic curvature up into its trace and traceless part. But this is where you would start from for the CCZ4 formulation. Okay.
Brackets, but is the end of on
Here.
right there. Now we have
Wait, hold on. Hold on.
Mine that was just supposed to be a parenthesis. right?
It is supposed to be a parenthesis. It's this parenthesis. And then where the heck is the end of the bracket? What did I do? It's right here. Sorry. Going too fast. Okay. So this is a common approach. I've got some stuff on conformal flatness here. We won't do that. The other thing that we wanted to talk about very briefly is the initial conditions. And so here, I'm not going to write anything on the board, actually. I'll just talk. That way we can spare ourselves some time. The initial conditions are a bit tricky for the binary neutron star mergers, like they are for almost any general relativistic system. So your initial conditions have got to obey the field equations, which means they've got to obey the constraints as well. And we talked at length about how you incorporate solutions to the constraints and the initial conditions for whatever problem that you want to solve, right? You'll have to deal with this when you're doing the TOV solutions to some extent, but it's very easy there when you're doing the TOED evolution, if we get that far with the final project stuff. Here it's even trickier because you've got these two stars, and for instance, one of the first choices you have to make is how are these two stars rotating relative to each other and relative to their binary orbits. The most common thing to do is say that they're irrotational, meaning that in the frame of any one of the neutron stars, it's not rotating, right? If you shift into that frame, right? That is probably the most common approach, but it suffers from a lack of generality because all neutron stars spin. And remember, we talked about this binary evolution path to getting these neutron stars where they swap mass and they're in a common envelope. All of those various stages will tend to spin up that neutron star. And so it's going to have a significant amount of angular momentum. And so irrotational works, and you can find a solution for it in GR, but it is not general. It's not quite correct. The other extreme, really, that you can write down a solution for it in GR is co-rotating, right? So the same face of the neutron star faces the other neutron star the whole time. It's like moon and Earth, right? Mercury and the sun, right? They're tidally locked, essentially. That's not necessarily what's happening in this case, but you make that assumption where their individual rotation rates equals the binary orbit rate, right? So they're always facing each other. The problem here is that that implies, especially as they get close, if you start close, they're spinning really, really fast, too fast, in fact. And so that's unrealistically fast. And so that is that's worse than irrotational. That's worse than irrotational in terms of physical applicability. And so more common is to choose irrotational. And then the other thing that you have to do when you're setting up the initial conditions for the field equations, the thing that's most commonly done, at least, is to assume that the spacetime is conformally flat. And that's nice because you can solve it. It reduces the complexity of the equations quite a bit. But here's the thing. What conformal flatness does is it does not admit any gravitational radiation, right? And so remember, the gravitational radiation comes from that metric perturbation to linear order, right, off the flat metric. But what you're saying in conformal flatness is that, no, that is the flat metric, right? And so there can be no H, right, union, right? You get rid of it. You can't allow it. And so there's no gravitational radiation in the conformal flatness. Cool, it allows you to set up initial conditions, but here's the thing with neutron star mergers. If they're a binary neutron star, they're going to be emitting gravitational waves. Always, all the time, no matter what their separation is, right? It could be vanishingly small amplitude, a very large separation, but they're always going to be emitting gravitational waves. And what we care about, even in, especially in binary neutron star mergers, is how the emission of gravitational wave leads to the merger, right? And so if you start from a conformally flat condition where there is no gravitational radiation, and you start from an irrotational initial condition, a problem that often crops up in these mergers is spurious eccentricity. And so the binary tries to respond to this, right? Because once you start evolving these things, the space-time says, oh, no, I have gravitational radiation. I want to emit gravitational waves. And so there's essentially an initial transient. And that can actually lead to spurious eccentricity of the orbit, an orbit that should be roughly circular. Really almost exactly circular. At any instant in time, it should be eccentricity of 0. We'll have non-zero eccentricity. And the system might not evolve that away. That could actually lead to some instability in the system. The other issue with those initial conditions where there's no gravitational radiation and the orbits are perfectly circular, you always assume that there is no radial component to the velocity of the neutron stars, right? They're instantaneously moving exactly tangentially to each other, right? Not in towards each other. But that's also not true because they're emitting gravitational waves in reality. And so they are falling in towards each other, in fact. And so that's another way that you incur this initial transient, which can lead to spurious eccentricity in the orbit. And so that's a problem. Now, if you are okay with that, and most of the time I guess we are in binary neutron star mergers, there's an open source code called Lorraine, and I put a link in the notes that you can use for generating initial conditions. It's what David used in all those simulations that I just showed you. It assumes conformal flatness. It assumes that initially there's circular orbits and there's no radial infall, there's no gravitational radiation. It's all very close enough. Now, for instance, and I think this is the case, and I think this is why those approximations that Lorraine makes are okay for like with the work that David was showing, or what I showed you from David. They start pretty far apart, and they go through many binary orbits. And so the gravitational radiation isn't that strong out here. And there's plenty of time for the initial transient to be washed away. It's when you're starting and you're only trying to do a few orbits maybe, that these problems of spurious eccentricity can lead to pretty different results. Now, if you can, in principle, solve the full field equations for your initial conditions, it's a lot more complicated, right, than assuming conformal flatness and all these various other fixes that we do. It's a lot more complicated, but you can do it. I've got some stuff in here about helical killing vectors, which is just another great band. But that's something that's often done in the initial conditions as well, because if you think about this in a space-time way, the initial conditions, especially if you enforce a conformally flat space-time, that means that there is a frame of reference that you could transform into where the binary system doesn't evolve, where everything is static, right? And that coordinate transformation is defined by a helical killing vector, right, in space-time. It looks like that. It makes a helix, right, as you evolve forward in space-time. Because of the symmetry, right? You're assuming a certain symmetry. And anytime there's a symmetry, there's a killing vector associated with that symmetry. So those are initial conditions. And I think what I'm going to do next time is just talk more about what happens in the evolution. We can revisit some of these issues of the aftermath of merger and tidal ejecta, et cetera, et cetera, et cetera. Questions? There's too much to cover in this topic. And I do think there were mistakes in this paper. I need to go and find a different source to look at.
It's in the.
Is it in the
Yeah.
Retzol and Zanatti?
Yeah.
Did they write it out in terms of the traceless split?
I believe so.
I like this because it elided over that complexity. But I think there was mistakes in the notation.
It's a box of equations. That's the point.
Yes. And ultimately not critical. Yes.
Yeah, but the gamma drivers.
Gamma driver. Yeah.
So you said it had the effect of decreasing.
Yeah, it forces it to go towards 0.
Okay, but the time derivative looks like it should be positive for
Which equation are you looking at?
so that's it, like so this one
Yeah.
or this
Yeah.
one has to be negative.
Correct.
So is it the second derivative? Or is it the time of
I see what you mean. I think it's the second time derivative. That's the
That forces the gamma, the connection function towards 0. So then if I look, and then, you know, I think maybe it would be easier to even see it from the first order equations. Maybe. Because then I could rewrite this in terms of an evolution equation for the connection function. Let's see that. I'm sorry, did I say towards 0? I meant that the time derivative goes towards 0. So it forces the connection function to be constant. I'm sorry. Thank you for pointing out that confusion. The time derivative of the connection function goes to 0. Thanks. That makes more sense. More sense than I was making. Other questions? A couple minutes. How are project numerical stuff going? Thumbs up. You had questions about Riemann solver. It needs to be tested now.
I've tested the Newtonian version. It
Yeah.
works. I was going to probably tomorrow night. Tonight's gonna be a nice day, and I need to. I'm still not used to it. So like this, yes, no one knows. But
Observe content.
I'm going to try and push my Riemann solver branch or something equivalent to that into your branch, like your
Or make a photo.
yeah, pull request so I can compare.
It's always better to let someone pull it and you just push it.
Okay. So yeah, we'll figure that out.
Okay. And so you thought that you basically just needed general relativistic inputs to
Yeah.
properly test it.
Because I tried to shove the general relativistic Riemann solver into a Newtonian framework, and that was
None of the units make sense then.
Yeah.
The characteristic wave speeds have no relevance.
The
in that case.
only major change is the wave speeds. At that point, you're just still being, u plus v over 1 plus u times v in units of c.
So do you want the test problem with shocks or weightless?
Any test problem.
TO
test it.
Yeah. Anything
Any
that
test problem to it.
works. Yeah. There are going to be two things to note. I do still need to remove. Right now, it is written in 2D format.
Okay.